over a video that went over the concepts in 5.1. It's a pretty easy section, so check that out. This video is going to cover 5.2. So I just wanted to hop on and give you an idea of what we talked about in class today. To give you a bigger overview, in the next 2 weeks, we're basically going to go through chapter 5 pretty quickly. I want you to basically try to understand the big concepts in 5.2. We're going to be able to use resources for the quiz and the test. But I really want to make sure that we understand all of the pieces of information that we are using for our resources. So that's what's most important about that. So what I'm going to do is I'm going to share my screen with you, and we're going to talk about, again, what we talked about in 5.2. So give me just a second here. Okay, so hopefully you all can see a blank screen right now. The first thing that I want to talk about in section 5.2 is a new term that we're going to use. And we're going to use some terms that we've used previously to kind of build on to learn what this is. So the term that we're going to be talking about in 5.2 is called the perpendicular, oh man, you guys know, perpendicular bisector. Okay, nope, that's not right. That's probably not still about right, but you guys know, the perpendicular bisector, right? So this is a new term. We haven't talked about this before, but you've heard the two words before. You've heard perpendicular and you've heard bisector. So basically we're putting those together all into one thing. So the first part we're going to work on is the bisector part. So to bisect something means to divide it into two parts. So we are going to take a line segment. Okay, so let's make a line segment here. And let me grab my pen here. We're going to make this line segment. We'll name it, I don't know, G and H. Okay, and we want to find the bisector of that line segment. And so we actually have a special name for the bisector of a line segment, right? We call that the midpoint. So that's what we want to find. To find the perpendicular bisector, we need to find the point that bisects our segment here. So we'll call that M for midpoint, fancy name, right? And M is the midpoint. And we could say that M bisects GH, which means that these two segments are congruent to each other. So we know all of this info so far, no new info, right? So that's the bisector part of perpendicular bisector. All right, so the second part is the perpendicular part. Perpendicular, we know, means to when we have two lines that are at 90 degrees to each other. And so we're going two lines, two planes, whatever it might be, that basically they're at 90 degrees. So if I drew something that's perpendicular, I'm actually going to draw a perpendicular, in this case, ray, that comes from the midpoint in this perpendicular. So let me do that really fast. Here we go. So now I have drawn a ray, right? And that ray is at 90 degrees. So that ray is perpendicular to my line. So now all of a sudden, I have a perpendicular bisector. So if I was using this in terminology, I would say that ray MP, and this, again, it doesn't have to be a ray, it could be a line, it could be a line segment, but ray MP is a perpendicular bisector to GH. So that's how we would use that. Ray MP is a perpendicular bisector to GH. And so now you know what that means. If something is a perpendicular bisector, there's two things we've got going on. It's perpendicular, meaning 90 degrees, and it bisects, meaning that it makes two equal segments by the midpoint. Okay, so now we know what that means, and we're going to build on that, and we're going to learn two theorems that have to do with the perpendicular bisector. Right. So the first theorem that we're going to learn is called Theorem 5.2, and this is called the perpendicular bisector theorem. The perpendicular bisector. we start with this base idea of what a perpendicular bisector is. So that's this right here, right? What we already did is perpendicular bisector. We think we should all know, kind of have an idea what that is. And this is what the perpendicular bisector theorem says. It says, pick a point, any point that's on my perpendicular bisector. So I could pick a point way down here. I could pick a point way up here. I could even pick a point down here that's technically on my perpendicular bisector. I can pick any point on my perpendicular bisector. We don't need to pick 3 points, so we're just going to pick one. Let's pick one kind of right in the middle. This point right here, which we'll call T, and T is on your perpendicular bisector, right? Now, if we play connect the dots and we go from the end point of my line segment to this point, and I play dot to dot on the side and go from the end point to this point T that's on my perpendicular bisector, I've made 2 new line segments. Think about, what do you think is true about GT and HT? Think about like kind of looking at that. What does that look like? Well, it looks like they're the same, right? And that's true. That's what our theorem tells us about perpendicular bisector theorem. So it tells us that GT and HT, since T is on the perpendicular bisector, that means that GT and HT are equidistant from point T. So they're equidistant from point T. So we don't actually use the word congruent when it comes to perpendicular bisector. We're talking about equidistant, which means we're not going to use the congruent sign. We're going to use the equality sign. So the perpendicular bisector theorem basically proves that if you have point T on your perpendicular bisector, that GT equals HT, that is true. Okay? So, and it doesn't have to be point T. Like I said, it could also be a point up here, right? We could call that point, I don't know, S. So then, again, if I drew up from my endpoint to S and from my endpoint H to S, then GS would be equal to HS. Also true. Okay, so that is our theorem, 5.2 perpendicular bisector. Don't forget to fill in your theorem sheet as well. So just to make sure that we've got it from your notes, theorem 5.2 is the perpendicular bisector theorem. And it says, in a plane, if a point is on the perpendicular bisector, so this is the perpendicular bisector, right? It divided CP is the perpendicular bisector because it's divided AB into 2, it's bisected, it's 2 equal segments, and it's at 90 degrees. So that means that C is on my perpendicular bisector, and that means that the distance from A to C is equal to the distance from B to C. Okay, so if I wanted to fill in my blank, it would say in a plane, if a point is on the perpendicular bisector of a segment, then it is, instead of saying congruent, we say it's equidistant, which basically means congruent, right? It's equidistant. So if it's equidistant from the endpoints of the segment, so these two are congruent. If CP is the perpendicular bisector of AB, then CA equals CB. Okay, so that's the first theorem that we're going to learn. The second theorem, we're going to go back up to this picture, and I'm going to use my magic tools of the computer here, and I'm going to erase the couple pieces of information that I have. Okay, just going to do that. Now, the next theorem that we're going to talk about, we start with this picture here. I'm like, hey guys, guess what? I've got line GH, and I've got another line or ray PM or MP, and I've got a point that's on PM that's T. And guess what? I figured out that GT is congruent to HT. So I'm starting knowing that. What do you think you can conclude about, is MP a perpendicular bisector or not? And that's what our second theorem is. It's actually the, well, it's theorem 5.3, okay? And it's called the converse of the perpendicular bisector. Remember, that means perpendicular. Converse of the perpendicular bisector theorem. So Do you remember what converse means? Converse means we're switching the hypothesis and the conclusion. So we're switching the hypothesis and conclusion from 5.2. In 5.2, we said we have a perpendicular bisector, so that means that the two segments that connect to a point on it are are equidistant. So the converse would say, if these two segments are equidistant, then MP is a perpendicular bisector. So it just flips that theorem and basically allows us to figure out if something is a perpendicular bisector or is not. So if I showed you this picture, right, and I said, is MP a perpendicular bisector to GH? You would say, well, based off this picture, because GT is equidistant with HT, then yes, it is the perpendicular bisector because of theorem 5.3, the converse. Okay, and again, so we're sure, make sure you fill in your sheets. It says if a plane, or in a plane, if a point is equidistant from the endpoints of the segment, then it is on the perpendicular bisector. Bisector of the segment. So DA is equal to DB. D lies on the perpendicular bisector of AB. So again, make sure you have those guys filled in. All right, so let's do two quick examples with this, and then there's one more thing that I want to share with you about perpendicular bisectors. Okay, so let's look at example number 1, which is right here. Okay, and we see here it says AC is the perpendicular bisector of BD. Find AD. So we want to find the length here. So if I know AC, let me make this a little bigger actually. Let's see what we're doing. Whoa. All right, there we go. Now you can see it really big. Okay. If we know that AC is the perpendicular bisector of BD, then we know that it's the perpendicular bisector, right? It divides BD in half, C is the midpoint, and it's at 90 degrees. And then on top of that, if we add in the perpendicular bisector theorems, we also know that the distance from A to B is the same as the distance from A to D. And that's how we're going to solve this, right? The distance from A to D is equal to the distance from A to B. And the distance from A to D is 4x, and the distance from A to B is 7x minus 6. I'm not going to do the math, but if you do the math there, you'll figure out that x equals 2, which would mean that AD is equal to 4 times 2, which is 8. And that would mean that that's equal to AB, which is also equal to 8. That's how we would use the perpendicular bisector. One more example, just to make sure you have it. Let's look at this one here that's a kite. Okay. This one here that's a kite. It says that KN, line KN, is the perpendicular bisector of JL. So here's JL, and here's KN. And KN is the perpendicular bisector. Okay? All right, let me erase some of that so we can actually see what's on our picture though. Right? There we go. We'll go back. There we go. All right, so it says what segment lengths in the diagram are equal? All right, so we know that KN is the perpendicular bisector. So we know then that means that JN has to be equal to LN. Right? This and this have to be equal because of the definition of a perpendicular bisector we just learned, right? All right, that's one. We also know that JK has to be equal to LK, right? JK has to be equal to LK. But that one's a little different. It's not just the definition of perpendicular bisector, it's the perpendicular bisector theorem that tells us that the two, we have point K that's on the line. So that means that if you connect from the end point to that point on the line, they have to be congruent. So, or equidistant, sorry. So that's the perpendicular bisector theorem. There we go. All right, so we've got JN has to be equal to LN, JK has to be equal to LK. And then there's one more thing. Look at this, the distance from K to M and L to M both is 13. So J to M and L to M, L to M, both equal 13. So that's just given to us, right? All right, so those are all the things that we can assume are equal. And then the second question is, and this is M down here. Sorry, I kind of wrote on top of it. Second question is M on KN? So is M on the perpendicular bisector, which is KN? So it's kind of hard to tell because the line stops, right? But if the line kept going, would it go through M or not? So this has to do with the converse of the perpendicular bisector theorem. The converse says that if you have some point M and it's equidistant from the two endpoints of your original segment, then it is on the perpendicular bisector. So we can, in fact, say, yes, M is on KN. And that is thanks to the converse of the perpendicular bisector theorem. Sorry, I'm running out of room here. So in case you're keeping up on that, the converse of the perpendicular bisector theorem is 5.3, and the perpendicular bisector theorem is 5.2. So that's how we would use one and the other. All right, so one last thing I want to tell you with perpendicular bisector. It'll take a little bit, but it's actually pretty interesting. So let's delete this off of here, and I want to ask you a question. Have you ever thought about how you would find the center of a triangle? So if I asked you to find the center of a circle, it's pretty straightforward, right? We just find where the center of the circle is. If I asked you to find the center of a square, that actually might not be too bad. Like if you try to figure out where the center of a square, might not be too bad to figure out, right? But what if I asked you to figure out where the center of a triangle was? How would you necessarily figure out where the center of a triangle is? Well, the answer is that there is actually more than one way to calculate the center of a triangle. And today you're going to learn the first way, but we're actually going to spend time figuring out several different ways to find the center of the triangle. Okay, and so the first method that I'm going to show you today is called finding the circumcenter of a triangle. So this is one of 4 ways that you're going to learn to find the center of a triangle. There actually are more methods than this. So you could go out there and research, and there's actually even more methods than just the 4 that we're going to learn over the next couple of days. But today we're just going to focus on the first one, which is finding the circumcenter. So let's have a little fun with this and pretend that we are throwing a Frisbee. So over here, we have Alex at point A, and he's throwing a Frisbee, and he's throwing a Frisbee over here to point B, which is where Beth is at. Okay, Beth has some longer hair. All right, looks like pigtails, right? And then up here we have Kathy. Kathy's got the ponytail. And the 3 of them are all throwing Frisbees to each other. Sorry, Alex, he's got a smile too. All right, they're all throwing Frisbee to each other. And, you know, the distance between Alex and Beth is not the same as the distance between Beth and Kathy, but they're in a triangle. They're throwing this Frisbee to each other. And I am the coach, and I want to stand in a spot that is equidistant from Alex, Beth, and Kathy. So I want to stand in the center of them. I want to stand somewhere that if I throw to Alex, it's the same distance as if I throw to Beth, and it's the same distance that I throw to Kathy. So how do I figure out where to stand if I want to be the same distance away from all 3 people? So we're actually going to use the circumcenter to find that, and that's one method of finding the center of a triangle. And so we want to figure out where can we be. The circumcenter is where you're the same distance. You're the same distance from all vertices or vertex, right? These are vertices. Remember, A, B, and C are your vertices. So you want to figure out where the same distance from all the vertices, and we're going to do that. You may have guessed this already. We're going to do that by using the perpendicular bisectors. You're like, okay, that's a little weird, but we're going to use the perpendicular bisectors in order to find the spot that is the same distance from all the vertices. And again, that's called finding the circumcenter. So the first thing we have to do is figure out where all of the perpendicular bisectors, sorry if I said angle, but where all the perpendicular bisectors are. So to find the perpendicular bisector from A to C, you got to figure out where the midpoint is. And I'm going to eyeball this a little bit, but you would use a ruler, right? And the distance from A to B, the midpoint looks to be about here. And the midpoint of C to B, the midpoint looks about here. Okay, so that I found all the midpoints, right? And I could connect those to find the mid segment. That was from last section, if you haven't watched that yet. If you connected all those, you would find the mid segment. But we don't want to find the mid segment. We want to find the perpendicular bisector. So now we have to draw a line from that midpoint that's at 90 degrees. So I'm going to do my best to make it look like we're about at 90 degrees. Looks pretty 90 degrees, right? 90 degrees-ish, that's hard to say. And then I'm going to draw a line here that comes at 90 degrees, okay? And I'm going to draw a line from here that comes at 90 degrees-ish. Okay, so I didn't do a perfect job because if I did a perfect job, then they would all actually meet up in one spot. So we're going to fudge it a little here. Oh yeah, we'll move that up a little bit. We're going to fudge it here. But if you actually drew the perpendicular bisectors correctly and measured really well, right? These are all perpendicular bisectors. And by definition, that would mean that these two segments, and these two segments are all congruent. If I do all that, they all will end up in one point here in the center. And that point is important, this red point right here, because that red point we're going to call, we're going to call that the point of concurrency. Okay, the point of concurrency. And that point of concurrency is really important because if I want to be the coach and I want to stand right in the middle of Alex, Beth, and Kathy, right, and I want to be the same distance away from them, I need to stand right here with my Frisbee, my long hair, right there with my Frisbee. And if I stand at that point of concurrency, I am going to be equidistant from all the vertices. So if I got out my ruler and I measured the distance from this point of concurrency to Beth, oh, I didn't quite make it to Beth. If I measured from my point of concurrency to Beth right here, let's say that was 10 feet, right? And then I measured from me to Alex. That's also 10. And then I measured from my point of concurrency to Kathy. That's also 10. So all of these three red segments that I just drew, they're all the same distance from the center, which I'm going to call the point of concurrency. Okay, so that's one way to find the center of a triangle is to use the angle bisectors to find that point of concurrency. And then once you do that, then from that point of concurrency to every vertex, it's the same exact length. All right, so technically, let's see how many lines am I up to here. I've got to do 4 lines. This line from A to P, A to P equals C to P, which equals B to P. So all of these 3 red lines are the same distance away. So we have a theorem for that, right? Of course. And that theorem is called the concurrency of perpendicular bisectors of a triangle. Okay, so this says that the perpendicular bisectors of a triangle intersect at a point that is equidistant from the vertices of the triangle. So if PD, PE, and PF are perpendicular bisectors, so this right here is a perpendicular bisector. These little, the green ones are the perpendicular bisectors, okay? They all meet at a point of concurrency, which is point P right there. Then if you go from point P in the center and you go out to the vertices, one is PA, and that's equal to PB, and that's equal to PC. They're all equal to each other. It's pretty cool. One way to find the center of a triangle. So a couple things that I want to tell you about this, and then we're almost done. One is that you might want to look at the page. I'm pretty sure it's the top of page 306. It's at the end of your 5.2 lesson. And there's an example of finding this point of concurrency for a right triangle, which is really interesting because the hypotenuse always has to go through the point of concurrency in a right triangle. There's an example for an acute triangle, which is what this is. And there's an example for an obtuse triangle. The interesting thing with the obtuse triangle is that the point of concurrency isn't even inside the triangle. So technically, to be in the center of a triangle using the circumcenter, your point of concurrency could be outside of the triangle. So if I had an obtuse triangle, if Alex, Beth, and Kathy were in an obtuse shaped triangle, I could possibly have to stand outside of the triangle in order to be equidistant from each of them. Okay. The other interesting thing, this is the last thing, and you're going to have to hope that I can do a good job drawing here. Think about this point of concurrency here and how each of these are equidistant away. And this kind of reminds you of radius, right? If you have a center point and every point is equidistant away, kind of reminds you of radius. And that's not it's not just a coincidence. So let's see, if I do a good job here and I draw a circle that goes through all of my vertices, pretty close. Let's just pretend Kathy's on that circle there. All right, not my best circle, but you get the idea, right? Here, we'll sketch it out a little more. That's what you do, right? When you want artists on there, you sketch it out a little bit. Okay. Keep making the circle, it'll get better. That's what we'll say. So if I make a circle that hits all of my vertices, it hits A, B, and C, right? I'm still, as point P, the point of concurrency, I'm still in the center, right? But all of a sudden, now if Dave wants to join our party, right? Dave also wants to be the same distance away from me, right? So he can play Frisbee. Dave's down here. If Dave wants to join in, we also think of that like a radius, right? And so if Dave wants to join in, he just needs to be somewhere along this circle that's made by connecting the three vertices. So what this is called, by drawing this purple triangle, that is called circumscribing. Nope, not a P. Circumscribing the triangle. Okay, so when we circumscribe the triangle, that means that we draw a circle around it and hit all the vertices. And that helps you kind of remember why we call it the circumcenter, because we circumscribe the triangle, which helps us to find the center of the triangle. And we do, the center of the triangle, which is also happens to be, if we circle around those points, then we find that. So again, to find the circumcenter, you use the perpendicular bisectors to find the point of concurrency. Once you find the point of concurrency, that point of concurrency is equidistant from all the vertices. All right, guys. So that's it. Thanks so much for watching, and I hope you guys are all well. Take care. Bye.